In the last video, we talked about a circle with a tangent to it, and we realized that the tangent is perpendicular to the radius that goes from the center to the point of tangency, the point where the line and the circle meet. And that was a really interesting fact about tangents. In this video, we're going to take a look at a different fact. So let's head back to the GeoGebra screen where I set up a slightly different diagram. This time, I've got a circle with center O, and I've got this point P that's outside the circle. And when I created the tangents, there are two different tangent lines, one that kind of goes above the circle and the other one that goes below the circle. And it kind of moves around depending on where P is. And A and B are the 2 points of tangency of those two tangents. And so what I've got here is I've got those line segment lengths. And so in this diagram, both of those distances are 19.7. Let me move point P around. So what do you notice? So the tangents are moving. The distances are changing, but the distances of the two tangents are always remaining the same. So that's an interesting conjecture. Let's see if we can prove that. And this is going to call to mind a lot of the triangle proofs we were doing in the fall. All right, let me start off by taking away some of these excess lines, and I'll draw a couple of extra lines. Because one thing that really helps us out when we're dealing with proofs is we know an awful lot about proving things about triangles. And so if we can put enough extra lines into a diagram to have some triangles, that's going to help us a lot. All right, so now we've got these facts right here. So what can we say? First of all, it looks, once again, as I move these triangles around, it looks like the top triangle and the bottom triangle are congruent to each other. So that would be an interesting thing to prove. Can I build up enough evidence to make that proof? So pause the video and look at the parts of the three circles, or sorry, the parts of the two triangles, and see which things we can actually prove are congruent to each other. I'm not just looking at things. So looking in GeoGebra, I can see that a lot of these distances are the same length as other line segments, but that's not a proof. That's just an observation. So what can we do to build a proof based on things that are logically certain? So hopefully you've given this a little bit of a thought. And let's take a look at this side right here. So this side is in both of the circles, or both of the triangles. And so I could say that it's congruent to itself, and that would be a side of the top triangle being congruent to a side of the bottom triangle. Do I have a reason for saying that something is congruent to itself? What would that reason be called? Well, that's the reflexive property. All right, so that's a valid reason to think that this red side is congruent to itself. Let's think about some other parts of these two triangles. Well, one thing, if I looked at this in GeoGebra, I would notice that these two things are the same size. Can I prove that they're both the same size? Not just from observing it and noticing that it's true no matter where I move P around. Let me take some things away to make it a little bit clearer. All right, I'll take away that side and this side and this side. Does this help it make it a little clear why we might think that those two blue line segments are congruent to each other? Well, what do they have in common? They both have O as one of their endpoints, and the other endpoint is on the boundary of the same circle. So these are both radiuses of the circle, and we know that radiuses of the same circle are always congruent to each other. That's the definition of what it means to be a circle. All right, so now we've got these two sides. There's a third fact that we can tell about this. We don't know that PA is congruent to PB. That's what we're trying to prove. So That's kind of the point of this triangle congruence theorem. I'll give you a hint. This third tip is something we proved in the last video. What did we show in the last video? Well, in the last video, we showed that tangents are congruent to tangents are congruent to the radiuses that meet them at the point of tangency. So these are both right angles. And so not only are they both right angles, but they're both congruent to each other. So both the top triangle and the bottom triangle are both right triangles. So now we've got 3 facts about these 2 triangles. We know 3 different similarity things about them. So that's usually enough to prove that 2 triangles are congruent. Now we've got 5 different reasons for being able to justify triangle congruence. We've got SSS, we've got SAS, we've got ASA, we've got AAS, and we've got HL. Which one of those is the reason we can use to prove that these 2 triangles are congruent? Well, SSS would need 3 sides, and we don't have 3 sides. We have 2 sides and an angle. So it's not SSS. It's not SAS because it has 2 sides and an angle, but the angle in SAS, the A is between the 2 S's. So we would need the angle to be between the 2 sides. And the angle between the blue and the red side is this angle. And we don't know anything about these 2 angles. We don't know that they're congruent. The angle we know that is congruent is not between the 2 sides. So we can't use SAS. ASA and AAS both need 2 pairs of angles, and we only have 1 pair of angles. So that leaves us with HL. We don't do a lot of talking about HL, but what does HL stand for? And can we use it in this proof? Well, the H stands for hypotenuse and the L stands for leg. So we need to have right triangles, which we do. Do we have congruent hypotenuses of these 2 right triangles? Yeah, the hypotenuse is this red side, and these blue sides is a leg. So because of HL, we can say that the top triangle is congruent to the bottom triangle. And once we know that these 2 triangles are congruent, we know that not just these 3 parts are congruent to each other, but the other 3 parts, all of the sides and all of the angles that we haven't shown so far in this proof are also congruent to each other. So let me color this fellow green and this other fellow green, because these would be corresponding sides of these congruent triangles. So because of that, CPCTC, corresponding parts of congruent triangles are congruent, that's enough for us to know that these 2 green sides have to be congruent to each other. And that is exactly what we wanted to prove. The 2 tangents to the circle are congruent to each other at the same point. All right, so that's the second interesting thing that we know about tangents and circles. First of all, that any tangent to a circle is perpendicular to the radius that meets it at the point of tangency. And the second is that if I've got a point outside a circle, the 2 tangents to the circle have to be congruent to each other. So those are facts that are going to allow us to prove an awful lot of interesting things about circles. We can solve some number problems from knowing those 2 facts. And I'll make a video where I go into a little bit detail of how we can use these facts, and that'll be our next video.